Alright, now it's quite important that we check our work after solving an absolute value equation, because there are times that we could end up getting what's called an extraneous solution. So I'll demonstrate this with the next couple of examples. Oh yeah, we just did this. We split our things into two cases, one positive and one negative. Alright, here we go with extraneous solutions. So let's solve a case like this. Our absolute value has already been isolated, so let's split into our two cases. As we remove the absolute value, we end up getting the right-hand side is a positive, well, let's just leave it in the original case, and the other situation is that it becomes the negative of what it was. The negative of a negative is, of course, a positive. And now I can quickly isolate our x. X is equal to negative 5 plus 2, or x is equal to positive 5 plus 2. And so x is equal to negative 3, or x is equal to 7. Now if I check these two answers though, if I substitute in, so here's my check, if I substitute in negative 3 into my equation, I end up getting the absolute value of negative 5, which is equal to 5. But I was supposed to get negative 5, so that check didn't work. I didn't get the right-hand side I was supposed to. Let's substitute in our other solution of 7. 7 minus 2 is equal to, so now I've got the absolute value of 5. That again equals positive 5, not negative 5. So both of the solutions that we found are extraneous. Although I went through the correct algorithmic process, I ended up getting answers that do not work in the original equation. Now, in fact, if we return back to the original equation, it should be fairly obvious why this is. We remember that an absolute value represents a magnitude, and we know that a magnitude must be a positive value. How can an absolute value ever equal a negative number? That's clearly a contradiction already. So although doing this algebra followed by a check would be one way of finding out that x has no solution, another clever way of doing this problem would be to make this observation right from the very beginning. So here's an alternative solution. We can observe right at this stage that an absolute value, and so we would need to write this comment in order to justify the absence of an algebraic solution with a check. An absolute value can never be equal to a negative number. And that is a nice justification as to why we end up with an answer of x has no solution without even writing down any numbers or equations. And the last example. Okay, this is obviously a lot more complicated. Let's begin by isolating the absolute value. So the first thing I can move to the other side of the equation is the negative 3 becomes a positive 3. And then I can move over the 4 to the other side by dividing everything on the right-hand side by 4. So my absolute value now is equal to, let's see, x over 4, which is the same thing as 1/4 x, and 2 plus 3 is 5, which is also being divided by 4. So I've divided every term on the simplified right-hand side by 4. Now I'm ready to take away my absolute value. So x plus 1 is, x plus 1 is either equal to the right-hand side as it appears, or remember it can also be equal to the negative of the right-hand side. So let's change it into a negative of the entire right-hand side. I'm going to put the whole right-hand side into parentheses as a reminder that I need to apply that negative to every expression on the right. Okay, now because these have got fractions in them, let's multiply everything through by the common denominator, which in this case is 4. I like getting rid of fractions early in my process so that I don't end up doing something silly. 4x plus 4, and on this side, if I multiply a quarter x by 4, it becomes a 1x, and this negative is distributing to it, so negative 1x. 5 over 4 times 4, that's going to be 5, and the negative is in front of it. Don't forget to distribute the negative sign. And now it becomes a pretty straightforward problem like before. We'll bring the x's to the left, and the constants to the right. So 3x is equal to 1, or 5x is equal to negative 9. And to finish then, x is either equal to 1/3, or x is equal to negative 9 over 5. But of course, I do need to check these solutions because there's a possibility that I got an extraneous solution while working on this. So I'm going to need to substitute these solutions back into the original equation to verify that the left-hand side and the right-hand side are equal. Now we have to be careful a little bit with our check. I must admit that the previous check in example L I did rather informally and casually. I'm going to do this one a little bit more formally. And so my left-hand side, if I first substitute in, so this is my check here, and just label that. So my left-hand side becomes 4 times the absolute value of 1/3 plus 1. I'm going to check that solution first. And equals 1/3 plus 2. So let's scroll down and, oops, I just realized I've done something a bit silly. I wanted to write down only my left-hand side. And then my right-hand side I'm going to write down separately as x plus 2, which in our case is 1/3 plus 2. Alright, let's simplify each side then. My left-hand side becomes 4 times, or 1/3 plus 1 is 4/3. And that's 4 times 4/3. And let's get a common denominator. I'll change my 3 to a 9/3. So I end up with 16/3 minus 9/3 gives me 7/3 on my left-hand side. On my right-hand side, let's get a common denominator. 1/3 and 2 is like 6/3, and that gives me an answer of 7/3. We can see that the left-hand side is equal to the right-hand side, and thus that is sufficient for us to conclude that x equals 1/3 is a valid solution, and we can keep it. I've got to do this check again now with x equals negative 9 over 5. I'm a little bit out of room, so I'm just going to cheat a little bit and just fill it in here. But hopefully you'll have space to be able to do that in another area of your sheet. And instead of substituting in 1 over 3, I'm substituting in negative 9 over 5. Wow, okay. Alright, so negative 9 over 5 plus 1 is negative 4 over 5. And the absolute value of negative 4 over 5 is, of course, 4 over 5. And this time, my common denominator is going to be over 5. So instead of a 3, let's change it to a 15 over 5. So I've got a total of 16 over 5 minus 15 over 5, and that gives me a final left-hand side of 1 over 5. On the right, I've got negative 9 over 5 plus 2. I can think of my 2 as a 10 over 5 if I get a common denominator. And that also yields a right-hand side of negative 1 over 5. So left-hand side does equal the right-hand side. In other words, both of my solutions, 1 over 3 and negative 9 over 5, both of these are valid solutions to the equation. If I had gotten a left-hand side not equal to right-hand side, of course I would have to discard that solution. Alright, now before finishing this video, I just want to show you how you can also use your calculator to solve some of these equations that we've been looking at. Going right back to the very beginning, let's do example A using a calculator solution. So I can go to y equals, and I'm going to enter in my left-hand side of the equation as y1. So that's 4x plus 5. And as y2, I'm going to enter in my right-hand side of the equation, x minus 1. Now I really want to find the value of x for which these two equations, or these two values of y, are going to be equal to one another. If the two values of y are going to be equal to each other, and I'm dealing with the same value of x in both equations, that means that I've got the same value of x and the same value of y. If you think of these as graph for a moment, I'm effectively then just trying to find the value of the x-coordinate where these two lines intersect one another. I can do this by pressing second, trace, and go down to option 5, intersect. The calculator asks me for my first curve. Currently y1, 4x plus 5 is highlighted. Yes, that's great. Let's hit enter. Asks me what my second curve is. It's my right-hand side of the equation, x minus 1. Yes, that's correct. Hit enter. And then the calculator asks me to guess. I can scroll over with the cursor so that I am right near the intersection point that I'm trying to find. I don't need to be exactly on it, just close. And I'll put enter, and it says that the intersection occurs when x is negative 2 and y is negative 3. Alright, so x equals negative 2. Well, that confirms what I had found when I did it using my algebraic method, that the x value was negative 2. I don't need this y value anymore, because that was an artificial variable I introduced to represent my left-hand side and my right-hand side. But in the actual problem, you see that there are no y's. We're only interested in the x value, where these two lines intersect. If you wanted to show your work on your paper that you had done this using a graphical calculator solution, a good way of doing it would be to write down y1 and y2. So your y1 is 4x plus 5, your y2 is x minus 1, and then you would just quickly copy a sketch of the picture from your calculator. And so in this case, our sketch would look something like this. That would be the y1 line, and the y2 line would look something like this. And we can see that they intersect right at this point, whose coordinates are negative 2, negative 3. And so you could draw this picture as your justification for x equals negative 2, instead of doing the algebra. One of those, now if you're not allowed a calculator, of course the algebraic solution is the manner in which we would expect you to do it. And I just want to go down to one other one. Ah yes, I just want to show you how to do example L as if it was a calculator problem that we wanted to solve graphically. And so I'll put in as my y1, let's clear that function, and I'll put in the absolute value of x minus 2. To get to the absolute value, we'll press math and come across to num, and it's option 1. So the absolute value of x minus 2, and my right-hand side is negative 5. So I'll clear the old function, negative 5. And if I graph these, there's my first function. That's what an absolute value function looks like, and that's what my constant function of negative 5 looks like. Clearly there is no intersection, and if you did try to find an intersection by doing second trace, option 5, intersect, yes, that absolute value function is my first curve. Yes, that constant is my second curve. Let's try to guess, get as close to a solution as might be possible, but when I press enter, we find out that no sign change, error, quit, and that again proves no solution for example L.